So the next flow meter that we are going to be looking at is the Coriolis flow meter. The ones that we have considered so far, they are volumetric flow meters, okay? But the Coriolis flow meter helps us, it's a mass flow meter, helps us to determine the mass of fluid that have gone through a section of the fluid. So this is the Coriolis flow meter, and the Coriolis flow meter, they work with the Coriolis principle. That is the Coriolis principle or Coriolis effect. That is the effect that a moving mass will have on a body in a rotating frame. So if you look at this Coriolis flow meter, it has a U section. Are you getting it? Inside this U section, we have two tubes. These are the tubes. Dual parallel flow tube. So the fluid does not go straight across. It is made to go through those dual tube, separated into two equal quantity or equal volumes, okay, or equal mass as the case may be, and made to go through the tube as you can see here, okay, before it is discharged downstream. So how does this flow meter function? So in this flow meter, we have a drive coil, okay, that helps to oscillate those two tubes, that create a vibrating force on those two tubes that makes the tubes to oscillate. Are we getting it? Then we also have an input and an output sensor. Okay, so the drive coil or the signal generator is here. Then we have input. If this is the upstream end, we have the input and we have the output. Okay, sensors. So how does it help us to measure the flow through this section? Now, ordinarily, when there is no flow across this, that is across through the tubes, okay, when the drive coil is energized, you see that those two tubes within this section of the flow meter will be vibrating. Are you getting it? So as they are vibrating, you see that the vibration is not distorted, so to say. So at this stage, as we'll see later, the signal that will be picked up by the input sensor and the output sensor will be in phase. Then when we start the flow of fluid through the meter, what will happen is that that mass movement of the fluid, okay, through the tube will have that Coriolis effect or twisting effect on the tube, as you can see in this second diagram. So you see that this the movement of the tube or the oscillation of the tube is not as smooth or as straight as that of the first one. You see the twisting effect, okay, on this tube. Are we getting it? So because of this twisting effect, we will now have a phase shift between the input signal and the output signal of the sensors, as we'll see later. So this is the drive coil, okay? These are the sensors, okay? This we have if the flow is from right to left, okay? This will be the input coil, and this is the output sensor. I mean to say, this is the input sensor and this is the output sensor. So since we already have flow, you see that Coriolis effect will cause that twisting of that tube, of those tubes, I mean to say, and that will cause the displacement of the signal generated or sensed at the input coil and the output coil. So that difference, the phase shift, is what we are interested in, because that shift is determined by the flow rate. As you increase the flow, the shift will be increased. Remember, as it is oscillating, as we saw earlier, okay, when there was no flow, you see that the oscillation is smooth, which means there is no shift between the input signal and the output signal. Are we getting it? The output pick up signal. Okay, so they are in phase. You see it, crest to crest, trough to trough, so they are in phase. But once there is flow, you see the Coriolis effect causing the twisting of the tube, as you have here. Okay, you now see that phase shift. See it, trough to crest, trough to crest. Okay, so that phase shift is determined by the flow rate, and that is what we have here. Okay, so delta t, this is the shift, okay, gives us an idea of the flow rate. Okay, so the shift is between the input signal and the output signal, the input signal and the output signal. So there is another quantity that we can also infer or measure from this meter, or with the use of this meter. Okay, and that has to do with the observed frequency. The observed frequency, okay, that is the number of oscillation per unit time that you see. So you see that if the fluid is dense, heavy, the frequency will be low, okay, because it will take greater force. Are you getting it? To oscillate, so the oscillation will be slow, and that will reduce the frequency. But if the fluid is less dense, is light, what will happen to the frequency? You see that the frequency will increase. It's just like the mass spring arrangement. Okay, when you have a spring and a mass at the end of the spring, and then you oscillate the spring. So you see that when you increase the mass, the oscillation, the rate of vibration, okay, the movement up and down, will do what? It will drop. Since it's heavy, to be slow. Are you getting it? But if it is light, you see it oscillating faster. That is exactly what is happening here. So the tube frequency is inversely proportional to the density. So when we measure these two parameters, the phase shift and the frequency, we'll have the mass flow, and then we'll have the density. And as we all know, density is mass per unit volume. Okay, so which means that we can calculate the volume from these two, that is volumetric flow rate, okay, from these two quantity. So if density is equal to mass over volume, or mass per unit volume, it means that volume is equal to mass over density. This is how the Coriolis meter work, and that is why it is very useful, okay, where we need to measure the mass flow rate of the fluid, okay, like in custody transfer of petroleum and petroleum products.